Now that we've talked about inertia and Newton's first law, we've talked about why we got some of the answers we did on that free fall tower assignment. I want to talk about how some of these concepts relate to one another. So we're going to talk about correlations. We're going to talk about direct versus inverse correlations. This is some vocabulary that you should know, and you're going to need to use it later on this week in our first lab. So, when we talk about correlation, we're talking about a possible relationship. Co means together. So how things relate to one another. That's what a correlation is. Between two, what we call variables. So a variable is just like anything you could measure. Right? Mass could be a variable, weight could be a variable, time could be a variable. Anything you could measure is a variable. So we're talking about how do two things we could potentially measure relate to one another. A direct correlation means that two things tend to increase together or decrease together. So a direct correlation
is this like a new topic?
It's sort of a new topic, but we're going to tie it back in.
It's a subtopic.
It's a subtopic, yeah. Direct correlation means two things increase together.
Can it be more than two things? Or does it only have to be two things?
You could have three things and compare two of them at a time. So direct correlation means two things increase together. One example of a direct correlation might be something like how much you study for an assessment and how high your scores are. Or how much time you spend practicing and how many basketball shots you make. So you think I can put practice on one axis and like skill on the other, right? Somebody like me, I practice basketball basically never. So if I go out there and I try to shoot a basketball, I'm gonna get, out of 10 shots, I'm probably gonna get 0 of them. Let's be realistic. I'm real bad at it. Does anyone here think they can get 10 out of 10 shots? All right, so like a couple of y'all are like, yeah, 10 shots. Yeah. Like,
It depends on from where though.
Yeah, you mean
so y'all are gonna be like here on the graph, where have you practiced a bunch? Those of you who do that?
no, they just have natural talent.
I don't believe in natural talent. Yeah, most of y'all who do that, you play basketball all the time. Gabby plays basketball all the time. Jacob plays basketball. I see y'all out there on the lower yard. So y'all, you're high on the skill and you're high on the practice. Who here is more in the mid-range? Like I occasionally shoot and I get some of the hoops. Right? You can beat me, but maybe not. Right? Y'all might be more like this on the graph. Right? But if we were to draw a line through this, we'd see this nice, straight, upwards pointing line. This is a direct correlation. Practice and skill increase together. The more you practice, basically anything, the more skilled you get. Right? That's a very clear, direct correlation. And there's loads of things we could change up on this graph. I could say, the amount of time I spend studying for my tests and my test scores. Right? The amount of time I spend playing first-person shooters and the number of headshots I get. Right? Loads of different things I could put on here. That's a direct correlation. Two things increase together. Can we stay focused on this back table?
Yeah.
All right.
Yes.
When it comes to our physics, we have a couple of examples of direct correlations. Mass is directly correlated with inertia. So if our mass increases, so does our inertia. Because inertia is a property of matter. Mass is also directly correlated with weight, which is also known as the force gravity on an object. So my capital F here stands for force, the G stands for gravity. So my weight, aka the force of gravity, will increase with my mass. The more kilograms I am made of, the more newtons of force, or the more pounds of force gravity is pulling me down with. So that's a direct correlation. We also have inverse correlations. And an inverse correlation means that as one thing increases, another decreases. We get over here?
Yeah, sorry.
So if I were to draw a graph of an inverse correlation, it's going to look very different from this. So direct correlations have lines that are slanted upwards. They have a positive slope in mathematical terms. Inverse correlations, the line is going to look more like this. So this could be a graph of the hours of sleep I get. Hours of sleep versus hours playing video games. The more hours I spend playing Baldur's Gate 3, the less hours I spend sleeping. This is a fundamental truth, as sad as it must be. I cannot simply, stay up all night playing games and still function the next morning.
Yeah, we'll give you an extension. What if you play
You would be surprised how often I dream of games like this, Raphael. I'm going to be honest.
I dream of playing games in my sleep.
Yeah.
You go to that.
All right. So that's an example of an inverse correlation.
That's so sweet.
Now, when it comes to the physics of this, mass and acceleration are inversely correlated. The more massive an object is, the less it will accelerate with the same force, with the same push or pull. Imagine pushing two shopping carts with equal force. One of them is full, one of them is equal. You give them both a push. The one that's moving fast, the one that's light, will move way faster. It will accelerate more than the one that is full. So, as mass increases, acceleration tends to decrease. Now, understanding the idea that there can be correlate. Oh yeah, Gabby?
What does the thing say? Or is it hours of sleep and I love this one?
Oh, hours playing video games.
Well, what's an example of an inverse correlation?
Amount of sleep I get versus the amount of hours I spend playing video games was the example I gave. Another example could be mass, how heavy an object is, and how much it accelerates with the same push.
So when mass goes up, acceleration goes down.
When mass goes up, acceleration goes down. Yes. Yeah, exactly.
No,
right?
that's not. That doesn't check
You have a
out.
limited number of hours per day.
It doesn't check out because also
Yes.
you said
So when you wrote mass goes up, then if mass goes up, inertia goes up, if mass goes up, weight goes up. What do we write for inverse correlation?
If mass goes up, acceleration goes down. Another example of inverse correlation, the less I eat, the more hangry I get.
same.
Right? So anger increases as food decreases. Right? That's an inverse correlation.
He gets more angry.
All right. The reason why we care about these correlations is because we can use them. So, almost all of you, I'm sure at some point in your life, have like gone to a doctor's office, stood on a scale, been weighed.
I have.
Here's the thing. Your doctor can tell you like, oh, here's how many kilograms your mass is. But they're not actually measuring. They're not actually measuring your mass directly, Joaquin. Because we can't actually measure your mass directly. When you step on a scale, it's not like doing a full body scan and being like, well, here's how many atoms you're made of, and if we add up the mass of all of those protons and neutrons and electrons, here's what your total weight is, right? A scale doesn't do that. Instead, a scale says, hey, the force of gravity pulling you down and how hard the ground has to push you back up to keep you from falling, those two things are directly correlated. So if I am 180 pounds and I stand on that scale, the scale pushes up with 180 pounds. The scale doesn't actually measure how strong I push down. It measures how hard it pushes up. It says, okay, I pushed up with 180 pounds of force, so that must be how much gravity is pulling you down. And on top of that, we know that mass and weight are directly correlated. So if we have your weight on a scale, we can find your mass. Because there is a direct correlation. And if I know, there's a line that describes that relationship. And if I know one point on this line, if I know your weight, then I can be like, okay, well, if this is how much you weigh, and I know you're on that line, you've got to be this particular point on the line. And that point on the line is this particular mass. So we can use this to figure things out. Yes, Raphael? No, you all have a weight. You have, there is a force with which gravity is pulling down on you, and that is your weight. Yes, Joaquin?
So if you weigh 500 pounds, the scale's pushing up 100?
Yes. Yeah. That's why scales have a maximum weight they're actually capable of measuring.
Because they can't push
Because
up.
they can't push up infinitely. All right. So, we actually we rely on gravity to find your mass. But what if we can't rely on gravity? For example, there are people who live in space.
Yeah.
Yes, there's many astronauts who live on the International Space Station. And the thing about living on the International Space Station is there's no gravity, right? It's also like not good for you to be living a long time without gravity. It does weird things to your body. And so if you've got astronauts in space, we need to monitor their health to make sure that they're not sick. So if they're sick or if they're losing weight, we need to get them back home, right? We need to get them back under Earth conditions where we've got like proper doctors and medical facilities and the like to take care of them. But at the same time, we can't just weigh them because there's no scale. So we use a correlation. Because mass is not only directly correlated with weight, it is also inversely correlated with acceleration. So we can just see like how hard is it to make this person accelerate. We can use that to figure out their mass. And so what we have in the ISS is basically an enormous spring-imaging. It's a thing that wobbles back and forth like this. You might need to adjust the angle. And the idea is, okay, if I've got this object and it's going to wobble, the fancy technical term for wobbling is oscillating. And oscillation is to move forwards and then back to the original position. That's one oscillation, which is just a fancy science word for wobbling. So we can time, hey, how long does it take this object to oscillate back and forth? And so, like, literally the astronauts get on the springy thing, it wobbles them back and forth, and it wobbles back and forth a certain number of times, and they have a machine that times them. It says, okay, how long did it take for them to do that? And the thing about this is you'll notice, if I take the mass out, this thing goes way faster, right? See how quick it is without an object in it? But the more mass in there, it slows down. And we have measured how long it takes a bunch of known masses to wobble back and forth in this thing. So we have the perfect graph that shows that relationship. And if we get a scientist up, or we get an astronaut up in there, we put them on this little wobbly thing. I mean, it's big enough that like an astronaut can sit on it. Yeah. This is a real thing that real astronauts do every day of their life. Look, being an astronaut is a very silly job in some ways.
Wait. So it's kind of like one of those like wobble skateboards, about like when you like stand on it, you go back and forth. Except it's
A little bit like that.
no, like for
Shucks.
If no one stopped you, would you just keep wobbling, right?
But there are going to be things.
Yeah.
Right, there's going to be friction in the machine and things like that that are going to slow down the machine. But yeah, so we time that, and then we can use this graph that shows the relationship. And what the graph is going to show is that you end up with a graph that's sort of like this, with time on one axis and mass on the other. And we make this line using a bunch of points that we already know. And then we get a time for our astronaut's weight that we don't know. And we know at the point of that line, so we can go down and figure out, okay, here's exactly how massive that astronaut is today. Is this a healthy weight or not? All right, tomorrow we will have our very first lab. You will need to remind me tomorrow that I have not had y'all do your hypotheses yet. Because the other classes I already had do their hypotheses. So please don't let me forget that. We will have our very first lab tomorrow. And in that lab, your goal is to figure out the mass of this little astronaut. This is an unknown mass. You're going to have a bunch of objects whose mass you do know. You're going to figure out the correlation between these objects, graph it, and use that to find this object's mass.